Hello everyone. So I am back again with yet another lecture of this course on aluminum based alloys and metal matrix composites. Okay, so let us start with a quick recap of the previous class. So if you recall, we discussed about the grain refinement by melt, vibration and stirring. So this is one of the ways of grain refinement during solidification apart from the melt inoculation that we talked about before. So here what you basically do is that the melt is physically stirred with some means such as mechanical stirring or electromagnetic stirring, and also at times you can apply ultrasonication. So once you do that, once you create that agitation into the molten metal, then that force which the molten metal is subjected to will lead to phenomena giving rise to grain refinement. Okay, so the mechanism through which that occurs, that is what we have discussed in the previous class. So these are the different mechanisms that we have over here. The shear fracture mechanism, for example, is related to the shear force caused by the stirring, and this actually leads to breakage of the dendrite arms. So this basically breaks the dendrites and multiply the grains. So you can say that this is a grain multiplication kind of mechanism which occurs due to the breaking of the dendrites into smaller fragments, leading to more number of grains into the melt. Okay, so that will lead to a higher number of nuclei also that will grow into solid. Okay, then we also talked about this grain boundary infiltration which occurs due to the bending, the plastic bending of the dendritic arm, which is again caused by the shear. So when the misorientation across the grain boundaries due to this plastic bending exceeds 20 degree, then the liquid penetrates the grain boundaries and leads to detachment of the dendrite arms from the mother grains. So this again produces more number of dendrites or grains and leads to grain multiplication, and as a result of that the grain size will be refined when the melt is solidified. Okay, but for this plastic bending to occur, we have seen that the relative motion velocity of the primary phase and the liquid phase should be large, and that is why the melt has to be agitated vigorously by one of these means. This is another mechanism that we talked about, the remelting of the dendritic roots, which occurs due to solute segregation. Solute segregation basically leads to a decrease in the melting point locally, and this would cause the remelting of the dendrite roots because the solute segregation primarily occurs near the roots, and therefore locally in those places the melting point would decrease and it would lead to the remelting of the dendrite roots, which in turn will lead to their breakage, giving rise to more number of nuclei in the melt. And then we also talked about another mechanism called crystal rain. This is basically the solid crystals which form on the mold wall, and due to their density difference, when these solid crystals fall back to the melt and get dispersed, they lead to a high number of nuclei and results in a high nucleation rate. Then we also talked about the ultrasonic cavitation process which is applied for grain refinement during solidification. Cavitation is a process of formation, expansion and collapse of bubbles in the melt, which basically leads to either a high nucleation rate or breakage of the dendrite arms, both leading to a higher nucleation rate or grain multiplication, and ultimately giving rise to a fine grain size in the solidified metal. And then we finally talked about this electromagnetic convection. So this is basically the electromagnetic field which is being utilized here. The force that is induced due to this electromagnetic field is known as the Lorentz force. And this is what leads to the sweeping away of the mold wall crystals and then dispersing them into the liquid metal, leading to more number of nuclei and hence higher nucleation rate, which will provide grain refinement. Okay, so these are the things that we discussed in the previous class. So today we are going to discuss mechanisms of grain refinement which can be operational in the solid state. Okay, so we are going to discuss some solid state methods of grain refinement in this particular class today. Okay, so far we have been discussing about the grain refinement into the melt during solidification. Okay, but there are certain methods through which the grain refinement can be done in solid state also, and these are basically done by applying a high amount of deformation, and such processes are known as severe plastic deformation. Okay, so that is what we are going to discuss right now and understand as to how this severe plastic deformation leads to grain refinement in different materials including aluminium and aluminium alloys. So severe plastic deformation is nothing but a process which can lead to a large strain into the material and deform it to a very large extent. Okay, so there are certain techniques through which this severe deformation or large strains can be generated into the material, and we have listed some of them over here. For example, you can see this high pressure torsion, which also goes by the name HPT in short. So this basically is a torsion kind of deformation that you could see over here in this particular diagram. So this is the workpiece that you have, which is being deformed in a die, and then it is rotated, and at the same time a vertical load is applied simultaneously on the workpiece. Okay, so as that occurs, it will actually lead to a torsion and generate a very high amount of strain into the material, leading to severe plastic deformation, and that would in turn lead to grain refinement. Okay, similarly, there is a process called equal channel angular pressing, or ECAP in short, that also leads to a very large strain into the material and deform it severely, leading to grain refinement. Okay, so all these things are done on a solid billet. As you could see, it can be in different size and shape depending on the die geometry. So here, for example, in the case of ECAP or even this high pressure torsion, you can use a cylindrical shape workpiece in the beginning, and then you can deform it in a die, leading to severe plastic deformation and grain refinement. So in such cases where the workpiece or the sample is deformed under a die like this, it is basically severe plastic deformation by shear with no change in the sample dimension in both the cases that you see here. Okay, so although you introduce a large amount of plastic deformation, the sample dimensions do not change. Okay, we'll talk about that in little more details in a while, but let us also see what other techniques we have for introducing severe plastic deformation in a material. This is another method that we have for the same, for introducing severe plastic deformation. This one that you see over here is known as cyclic extrusion compression, or CEC in short. The second one that you see here in figure B, that is known as continuous cyclic bending, and the third one that you have over here is known as repetitive corrugation and straightening. So here you can see, this is a process, the first one, cyclic extrusion, which basically involves a number of extrusion cycles, as the name itself suggests, to accumulate the strain in the material and ultimately deforming it severely. Similarly, in the continuous cyclic bending, the material is deformed between the rolls continuously in a number of cycles. And in the repetitive corrugation and straightening technique, the workpiece is first bent into a corrugated sheet, as you could see, and then with the help of these straightening rolls, it is again straightened. And this process is repeated for a number of cycles, and as you do it, more and more strain is accumulated into the material and it is deformed severely, leading to grain refinement. Okay, so all these processes that you see over here in these three figures basically lead to severe plastic deformation by large accumulative strain through repetitive deformation, right? So here, as you increase the number of cycles of deformation, the strains accumulate, and that ultimately leads to the severe plastic deformation, which the material is supposed to be subjected to for the grain refinement to occur. So this is a repetitive process which is done in number of cycles. Then here we have another process which again goes through number of cycles, or the strain here also is accumulative. The process is known as accumulative roll bonding. So here it not only leads to severe plastic deformation, but can also lead to bonding between two metallic sheets, as you could see, which the name also suggests, right? So the process goes like this, as depicted in this particular diagram. So you have a stack of pre-rolled sheets, as you could see. First you cut the sheets in the required size, and then they are stacked together, and this stack of rolled sheets are then subjected to rolling. And as the rolling is done through several passes, it will lead to bonding between these sheets and also severe plastic deformation, which would ultimately lead to grain refinement. But for this bonding to occur, this can be done at higher temperature. Then we have this process which is relatively new. The process is known as friction stir processing. This is basically a variant of friction stir welding. So here, instead of welding, the same tool is used for processing the material. Okay. So when you do welding, you will have two plates to be joined together with the help of a tool like this, okay, which has a shoulder and a pin. Okay. So what is done over here is that this pin of the tool is actually plunged into the workpiece, and then a load is also applied simultaneously. A vertical load is applied simultaneously, and the tool is rotated at high speed. Okay, so as this pin plunges into the workpiece, the shoulder will touch the workpiece surface, and as the tool is rotated at high speed, with the simultaneous application of the vertical load, a large amount of frictional heat will be generated at the tool workpiece interface, and that will actually first soften the material, And since a vertical load is also applied, once the material is plastic enough, once it is plasticized, then it will start to deform. And then as the tool is moved in a particular direction, like this, with a particular traverse speed, the material will be subjected to severe plastic deformation and it will be processed. Okay, so the material which is left behind the tool as it moves will be a processed material which has gone through severe plastic deformation and will be having a finer grain size compared to the base material which is not subjected to any deformation at all. Okay, so if you have welding to be done, then as I said, you will have two plates and this tool will be moved along the joint line leading to a joint between the plates. But in case of friction stir processing, only a single plate is used. So all the energy, all the mechanical energy of this tool is gone into deforming the material, leading to grain refinement. Okay, and the temperature in this case can go up to 80% of the melting point, and hence you can say that this is a thermomechanical process, right? Thermomechanical process, as you might know, is a deformation process which is done at high temperature. So as I said, this is the stir zone which is subjected to severe plastic deformation. So this will have a fine grain size. But apart from this stir zone, there are different other microstructural zones having very definite microstructure around it. For example, just adjacent to the stir zone, you have a zone known as thermomechanically affected zone, okay, or TMAZ. So this zone also is subjected to high temperature and deformation, but the extent of deformation or the degree of deformation here will be lower compared to the stir zone. And then next to it, like any other welding process in this friction stir welding or friction stir processing also, you have this heat affected zone, which is the region that is subjected to heat cycle but not any deformation, right? So this will display, this particular region or has will display a coarser grain size compared to the other two regions, right? So these are the different techniques by which grain refinement can be carried out in solid state. And many of these, in fact, have become very popular for grain refinement of aluminium alloys. So now we'll talk about the mechanisms of grain refinement as to how exactly this plastic deformation, this severe plastic deformation leads to the grain refinement. Okay, so we'll take an example of the ECAP process that we talked about before. This one. So this is severe plastic deformation or SPD by shear. Okay, so you can see, the die has a particular angle between these two ends, the end in which the workpiece is inserted and the end through which it comes out. Okay, so there is a particular angle between these two parts of the die. So this is the workpiece which is inserted into the die, and now it is pressed with the help of a plunger like this. So as you apply a load through this plunger, this material will be deformed inside this die, and then through this angle it will come out from the other side, okay, without any change in the dimensions, as I said before. Okay, so although a large amount of strain and deformation is introduced into the material through this plunger and the load which is applied to this, there will be no change in the dimension of the workpiece. Okay, so now let us see what is going to happen due to this kind of deformation that the material is subjected to in a die like this. So as far as this ECAP process is concerned, there are different routes or different ways in which the workpiece can be deformed inside the die, okay, and that depends on whether it is rotated between the passes, okay. So what is done in this case is the billet or the workpiece is deformed through a number of passes, okay. So you can say that it is a multi-pass process for you to obtain a large amount of deformation in the material, okay. So now what is done in between the passes, between two consecutive passes, that would give rise to a particular type of ECAP process, and these are given names like this, these different routes of ECAP. For example, route A, that is pressing with no rotation between passes, so that you can see over here in the first picture of this particular diagram, okay. So you in the first pass you deform the material, take it out, and then again you insert inside the die without rotating it. Now if you rotate it, then you have the other ECAP routes. For example, in case of route BA, the workpiece is rotated 90 degree in alternate direction between passes. That you can see here. So this is the first pass, and then in the second pass it will be rotated 90 degree in one particular direction, and in the next pass it will be again rotated 90 degree but in the other direction. Then you have route BC, which involves a 90 degree rotation in same direction between passes, as you can see from here in this particular diagram. And then you have route C, which involves 180 degree rotation between passes, okay. That is again shown in this particular diagram also with the help of an element. A small element is shown as to how it deforms as the workpiece is rotated between the passes. So in route A, as I said, there is no rotation at all. So you can see how a particular element inside this billet will be deformed as the number of passes increased, okay. And then here in the route B, it is rotation in alternate direction between passes. So this is the first pass, and then it is rotated 90 degree in the next pass, and again 90 degree in the opposite direction, and so on, okay. And BC is 90 degree rotation in the same direction, as you could see. This is the first pass, then 90 degree rotation in the second, then third also again 90 degree rotation in the same manner, and so on and so forth, okay. And in case of route C, you can see it is rotated 180 degree. So if you look at the character of the slip or the deformation between the passes as the billet is rotated, you can see, for example, in route BC over here, the deformation or slip in the first pass, which is here, is cancelled by slip in the third pass. That means the direction of slip in the first pass and in the third pass will be opposite to each other, okay. And in case of route C, which involves 180 degree rotation between passes, the direction of shear is reversed on each pass, right, because it is complete 180 degree rotation. So you can see the deformation direction or the shear direction is reversed between any two passes, okay. So a particular element inside the material is subjected to severe plastic deformation in different ways depending on how the billet is rotated between the passes. And as I said before, this is deformation by shear, and that can be shown with the help of a diagram like this. Again, selecting a small element inside the billet and looking at it as to how it deforms as the number of process is increased. Okay, and all the four roots are shown over here: A, BA, BC, and C. And the same element is being shown as to how it deforms in different ECAP roots. So you can just note this X, Y, and Z planes. Okay, and now you select any small element from this billet and see, as we increase the number of passes, how that particular element deforms in this X, Y, and Z planes. Okay, so this is the X plane, this is the Y plane, and this top one is the Z plane. Okay, so in case of root A, we know by now that there is no rotation at all. It is just simply inserting the billet into the die and then subjecting it to deformation through a number of passes. So this is how it is in the beginning. No deformation in the beginning, and then in the first pass, let's say you are inserting in this manner, right, as it is shown here. The element on the X and Y plane is deformed, and as you keep on increasing the number of passes, this degree of deformation on these two planes also increases. As you could see from these elements, they become thinner and thinner as the number of passes is increased. But one thing that you can note over here is the fact that on the Z plane there is no deformation at all. Okay. Now let us look at root BA, which is alternate rotation by 90 degrees between passes. So this is in the beginning, and then in the first pass it is deformed like in root A on the X and Y planes, and now it is rotated by 90 degrees, and therefore the Z plane will also be subjected to plastic deformation here, unlike the root A where this plane remains intact without any plastic deformation, plane Z. Okay, but here, since there is a 90-degree rotation involved, all the three planes will get deformed in root BA. Okay, in root BC, on the other hand, it is rotation in the same manner, in the same direction by 90 degrees between passes, right? So here first it is deformed, and then it is rotated 90 degree, another 90 degree, and then another 90 degree. So when you come to 1, 2, 3, the fourth number of pass, you can see that the element is restored again. So this is what I said before. If you remember, in case of root BC, the slip in the first pass is cancelled by the slip in the third pass, and therefore in the fourth pass it will be back to the original condition, right? And in case of root C, it is 180 degree rotation. So in every one pass, every single pass, the element will be restored. Okay, so that's what I said before also. It's a redundant process. The deformation is redundant because the direction of shear is reversed in each pass, and every second pass the element, any element inside the material is restored. Okay, because here the rotation is by 180 degree in the same direction. Right, so this is how, with the help of this particular diagram, you can see how the shear deformation leads to accumulation of large strain into the material, and this will actually lead to refinement in the grain size. Okay, so in order to understand how exactly the grain refinement occurs, apart from this physical picture that this particular diagram depicts, you will also have to look at the dislocation mechanisms. Okay, so if you remember, I had said that this dynamic recrystallization which occurs in the material can play a very important role in the severe plastic deformation process. So we'll have to look at that also as to how this particular phenomenon, dynamic recrystallization, plays a role over here in case of severe plastic deformation to refine the grain size. That will be our next topic of discussion. But for today, this is all I have. Thank you for your attention.